Right, I see we are recording. Okay, so I'll be talking to you about the misuses of p-values and hypothesis testing, and also hopefully providing you with some potential solutions to these problems. In terms of my background, I've been working as a consultant biostatistician and lecturing in biostatistics for close on 20 years at various medical schools. And during this time, I've collaborated with and consulted with many different researchers and clinicians in many different departments across a wide variety of domains, diseases, and conditions. So this talk will draw on my firsthand experiences as well as extensive research by top statisticians over this time, and with links to trends to this worldwide revision of statistics testing, which is currently gaining momentum. I also wish to acknowledge my colleague, Professor Lehana Thabane, and his talk, Statistical Significance to Clinical Relevance, Time to Get Rid of Significance. So I actually cannot advance my slides at the moment, so I'm just going to get out of this view. I'm just going to stop sharing my screen for a minute. Sorry. Right. So this revision or overhaul of the way that we apply, teach, and use statistics to interpret research data is what's currently up for debate. Although this is not a new problem, the world started to take notice after this particular publication in Nature last year, which actually included more than 800 signatories by prominent scientists, statisticians, and researchers. The article summarized the main problems related to statistical significance, such as the incorrect interpretation of p-values, leading to false conclusions and unreproducible studies. They recognize that the problem is not necessarily with the p-value itself, but in the way it's used, mainly the categorization of p-values into statistically significant or not, and they called for an end to the term statistically significant. I'll just start with a brief history of null hypothesis statistics testing. So NHST stands for null hypothesis statistics testing, and p-values, just to sort of set the scene and see where we came from. Currently, this is the most common approach used in the frequentist paradigm of data analysis. The approach has actually been criticized since its proposal, but nevertheless has been adopted as a sort of a standardized approach and used blindly nowadays in research and testing and teaching. Building on what previous statisticians had discovered, Carl Pearson at the turn of the 20th century and Ronald Fisher slightly later, formulated the modern significance paradigm, and they published tables that made statistical testing possible for the average researcher. Remember that this was a time before modern computers and software. Fisher noted that p less than 0.05 was a convenient cutoff level, as it approximated equivalently 2 standard deviations from the mean in a normal distribution. He also noted that there should not be a fixed level of significance for all situations. Indeed, many of Fisher's colleagues also raised doubts about significance testing, as are being raised today, suggesting that it is not a new issue. It's not difficult to understand how in these times when modern computing methods and software were not available, a p-value or an alpha of 0.05 became the criterion for judging statistical significance. Slightly later, Neyman, and this time a different Pearson, framed hypothesis testing using 2 competing hypotheses, the null and the alternative hypothesis, in a decision theoretic approach. The current null hypothesis statistics testing merges the approaches of Fisher and Neyman Pearson. So the problems that I'm going to be talking about today are the misinterpretation of p-values, the inappropriate use of null hypothesis statistics testing, the temptation of p-hacking and all that goes with it, the problem of not giving enough details in order to be able to interpret p-values in published articles, and what I feel is the underlying problem, academic pressure. Starting with the misinterpretation of p-values, a big problem is that the p-value is not a concept that is really easy to explain or to understand. In fact, statisticians themselves have a hard time explaining p-values. The American Statistics Association, or ASA, gathered 26 experts to develop a consensus statement on statistical significance and p-values. And not surprisingly, they couldn't agree on one definition, and they debated on this topic for more than a year before they finally produced the consensus statement, which goes something like this. Informally, a p-value is the probability under a specified statistical model that a statistical summary of the data would be equal to or more extreme than its observed value. I'm sure you'll agree with me that this definition is about as clear as mud. Another problem is that people think that a p-value tells you if your hypothesis is correct, but in fact a p-value cannot tell you if your hypothesis is correct. It is in fact the conditional probability of your data given the hypothesis, which cannot be changed around to say that it's the probability of the hypothesis given the data. I'll illustrate this with a simple example. You could ask the question, is the Pope Catholic? To which the answer would be yes. But if you switch that statement around to say, is Catholic the Pope? The answer is probably not. So the statement doesn't survive the other way around. P-values can also not tell you about the size of the effect. In other words, they cannot tell you about the clinical significance of your results. Statistical significance is not equivalent to clinical significance. Small p-values do not necessarily imply the presence of larger effects and vice versa. Any effect, no matter how tiny, can produce a small p-value if the sample size is large enough. Following that statement, non-significant results also don't mean the absence of an effect. If we remember the famous statement, absence of evidence is not evidence of absence. This is an example of a type 2 error. And conversely, overpowered studies can lead to statistical significance without clinical relevance, which is the possibility of a type 1 error. These problems highlight that the correct use of statistics requires an attention to detail that regular scientists have tried to get around by using shortcut definitions and interpretations that are sometimes downright wrong or misleading. In conclusion, most statisticians agree that p-values are not to blame. However, the improper use of p-values and null hypothesis statistics testing is to blame. A quote from Ashwanden 2016 says, p-values are not badges of truths, and p less than 0.05 is not a line that separates real results from false ones. There's simply one piece of the puzzle that should be considered in the context of other evidence. Moving on to the second problem, inappropriate use of null hypothesis statistics testing. This is actually a concept that's quite difficult to explain in this sort of a seminar, so I'll just be quite brief about it. In Lehman and Pearson, when they devised or optimized null hypothesis statistics testing, it was designed to work efficiently in the context of a long run of many repeated experiments. If we only run one study, all we can claim is that this would be the type 1 and type 2 error rates if we had run a long series of repeated studies. So it's very difficult to actually do anything with one particular study, and not one particular study should actually be used on which to base evidence for change in policy and practice. Secondly, the null hypothesis is usually, researchers usually set this to zero effect, and they usually do not quantitatively define the alternative hypothesis. Therefore, they are always comparing the alternative, whatever it is, to zero, and not to the smallest non-clinically important difference, which might or might not have been defined in a sample size calculation. It's nullism. So Sander Greenland, a very prominent statistician and epidemiologist, last year said that the null hypothesis statistics testing problem arises from a synergy of dichotomania and nullism. Dichotomania is the propensity that humans have to put things into boxes, to label them as black and white. In other words, statistically significant or non-statistically significant. Okay, so thirdly, I'm going to go on to the temptation of p-hacking. So there's one golden rule with data analysis, and that is that data analysis should be done as planned in the research proposal or protocol, which was designed prior to data collection or prior to seeing the data. If you do not do this, there's a good chance that your results will be influenced by bias, which means they will not easily be reproducible or repeatable. But more importantly, it means that they could actually be false. John Ioannidis claimed this in 2005 when he said, an overwhelming number, over 90% of published articles report p-values of 0.05 or less, and many of these claims are likely to be false. So p-hacking is an umbrella term for many terms which include ad hoc sample size selection, hacking, cherry picking, and more. Ad hoc sample size selection differs from planned adaptive sample size methods that compensate for alpha spending. Ad hoc sample size is where you would not define your sample size in advance, but keep sampling until you like the result and then stop. Hacking is hypothesizing after the result is known, and this is where you test many associations. You maybe find one that you like, and then you publish that as though it was the original hypothesis. Also known as double dipping, where you use the same data to generate hypotheses as to test them. Others include cherry picking, where you choose to report the results that support your hypothesis and ignore those that do not. Sometimes people measure multiple response variables so that they can choose which ones to report on post-analysis and drop the ones that they don't want to report on. There's other forms of p-hacking also, which include deciding whether to include or drop outliers post-analysis, excluding, combining, or splitting treatment groups post-analysis, excluding covariates post-analysis, and stopping data exploration if an analysis yields a significant p-value. I think that a lot of researchers do this quite innocently, not, as the name suggests, p-hacking sounds like a insidious and a bad thing that you do on purpose, but I think a lot of people don't realize that it's not right to do this, and they just do it anyway because they don't realize that it is a form of research misconduct. This diagram demonstrates the many forms of p-hacking. If we start at begin and we analyze the data, if the p is less than 0.05, we sometimes stop, or if not, we could go on and do any of those that are listed there and go and loop back to analyzing the data and starting all over again. When you p-hack, the results cannot be interpreted at face value because you've actually introduced bias into your results. Hacking is the other problem that I spoke about. Here, the researchers, after failing to reject their original hypothesis, test 20 subsamples and find that one of them p less than 0.05, and they publish only that result, leading the public to believe that this was their original hypothesis. They also failed to adjust for multiple testing. The jelly bean example, they first tested an overall hypothesis, jelly beans cause acne, and they found that p was greater than 0.05, so they refuted that, and then somebody said, oh, it's the different colors of jelly beans. So they tested all 20 colors, and they found only green jelly beans are linked with acne, and they failed to report all the other colors that weren't associated, and they only reported that green jelly beans were linked with acne. The fourth problem is that details are sometimes not given. The problem is that you cannot just interpret p-values and results of statistical tests without knowing the context behind and the sampling that was done and the whole methodology that was used in enough detail to allow reproducibility of the study. P-values are only meaningful when you know how the sampling was done, when you know the context behind the study. And often sample size justification and the minimal clinical important difference, MCID, are not given in either the protocol or in the methods section of the publication of the results. All of these and more will need to be given, and I'll be spending quite a lot of time talking about which details and openness and honesty need to be supplied before you can actually understand and interpret p-values. And they're not meant to be interpreted at a face value on their own without a context. So getting on to the fifth problem, which I think is the underlying problem for all of this, and that is academic pressure. To understand this, we should first consider the nature of the academic industry in which research takes place. Reward is largely driven by publication output, which leads researchers to choosing to do studies that they know will lead to statistically significant results, rather than studies that are actually interesting, novel, or urgent questions to answer. Publication bias, whereby journals selectively publish studies showing small p-values, even in the presence of small effect sizes or minor clinical differences, which are possibly type 1 errors, is a major driving factor in the vicious cycle, which can then lead to p-hacking and other conscious or unconscious methods of falsely increasing the likelihood of a p less than 0.05. Additionally, and something that I've felt my entire working life, is that where consultant biostatisticians are employed at academic institutions to consult and collaborate with researchers, even adequate training might not prevent misuse of the null hypothesis statistics testing. In the intensely pressurized academic environment where consultant biostatisticians have less than optimal time to acquaint themselves with all the details and clinical information each study requires, many statisticians are guilty of simply applying this paradigm mindlessly. They might also be guilty of trying to please the researcher or having undue pressure placed on them by the researcher who is desperately trying to find something worth publishing in all their hard work. A survey of consultant biostatisticians revealed that researchers frequently make unethical requests on biostatisticians, including changing the data to support the hypothesis. Researchers resorting to the extreme measures to get a publication, such as data fabrication, has resulted in many publication retractions, which have serious consequences. So I'm going to share with you a personal example of my experiences in my early days as a biostatistician and all the mistakes that were made. This is way back in 2003. I think I was just recently qualified and just in my first job as a biostatistician at another university. This is not Stellenbosch University. This is not Western Cape. I'm not going to mention any names though. This is before antiretrovirals were available in the public sector to treat HIV. And I was involved in a clinical trial, my first clinical trial ever. And we made almost every mistake in the book. Well, luckily, some of the mistakes we were prevented from making. But I think it's a good teaching example. And I do, apologies if there's any of my students in the room today, because they might have heard this before. I use this all the time in my teaching. So what happened was a Russian scientist invented a device based on electromagnetic waves at the right frequency to disrupt the HIV virus particle in vivo. In vitro tests in animals showed that it was safe, so he sold the technology to a company that wanted to make money to cure HIV. So the company actually did start using this device until they were told, no, they need to have a clinical trial, they need to get the relevant authorities' approval, the MCC at that time, and the evidence needed to be based on a clinical trial. So they got our university involved in a clinical trial, and I was the statistician on the team. I was really excited because I wanted so badly to be part of the team that cures HIV. It was a very large team of researchers, clinicians, basic scientists, etc. We didn't have any pilot trial data on how long the patients should be exposed to the device in order for it to work efficiently. So we designed a double-blinded, dose-ranging, sham-controlled trial. Those randomized to the sham group would sit in front of the device when it was turned off. You can see in this picture, this is the sort of treatment rooms that they used. The device is in the middle of the room, it's all those boxes there, and the patients would sit on chairs all the way around the room. Some of the patients were very sick, they were lying down. Yeah, it was quite bad. The outcomes were the participants' HIV viral loads, their CD4 counts, other biochemical measures, mortality, morbidity, and many other outcomes, including quality of life. These were all monitored over a period of a year. So after collecting the data for a year, our primary analysis revealed a 0.25 log decrease in HIV viral load in the treated groups over and above the sham group, which was statistically significant at the 0.001 level. Luckily, before we could get excited about this result, the virologists on the team pointed out that this difference was not clinically important at all, and that with ARV drugs, a 1 log or more change over this time period was expected. So luckily, we avoided making a type 1 error. The problem with the design was that our primary analysis was collapsing all the treatment groups at different doses of the exposure into one group to compare them with the sham. This made our sample size very large, and we were able to detect very small, clinically unimportant effects. We also did not see any clinically or statistically significant effects for any of the other outcomes measured, except for apoptosis, but none of the clinicians or basic scientists could explain whether that would be a benefit to the patient or not. So, of course, we were all devastated as we were holding out much hope for this as a treatment. I had to present the results to the company and their funders, which was extremely nerve-wracking, and needless to say, they were not happy with me at all. They hired another statistician from the USA to come and work in South Africa with me to try and find holes in my analysis. They basically sequestered the two of us in a room for 3 weeks where we went over everything again, and luckily, thankfully, he reviewed my work and could not find any problems with my analysis. The company then ordered a series of subgroup analyses based on trends that we had seen in the data, like what if we just look at men over 50, or what if we just include those with severe disease to begin with. So I was so wanting to please them and to show something that I was naive enough and I had not heard of p-hacking or harking, and I graciously complied with all their requests. Fortunately, the more experienced USA statistician advised me against it, and we took a stand against the company. We were then prevented from publishing any results by the company, who then continued to use the device to treat patients until they were discovered and closed down. Actually, Treatment Action Campaign was instrumental in closing them down about 8 years after this trial, because ARVs were then available. But you know what the situation in South Africa at the time was, that ARVs were poisonous, and there was much controversy even within our government about the use of the efficacy of ARVs. So yeah, eventually this company was closed down. Their website states that a large clinical trial found the device to be safe for humans. It does not mention that there was no clinical benefit found. Okay, I promise you I haven't made anything up. That is completely real, and a very good learning experience for what not to do. So moving on to possible solutions to all these problems. So in 2020, we are now standing at a crossroads following this ASA publication in 2016 and the schools of thought that have emerged out of it, driven largely by American statisticians. In 2019, the same journal delved deeper into this issue with a special edition containing more than 40 essays on possible ways to address this challenge. Some of the solutions are removing or banning p-values, which I'm not going to talk about because I think most statisticians agree that there is a place for statistical testing, but the fault lies not with the p-values themselves, but how they're misused. The second solution is to remove that 0.05 threshold. Third is to change the threshold from 0.05 to 0.005. Presenting additional metrics over and above the p-value or instead of the p-value. And lastly, improved reporting and interpretation. The second solution to remove the 0.05 threshold, this particular paper here, Moving to a World Beyond P less than 0.05, was the editorial to the special edition, which summarized all 43 papers. And in summary, it basically said to avoid saying statistically significant, to treat p-values as continuous measures, that is to report the actual p-value along with the full details of the study in an open and honest way. The third proposal by this huge group, if you can see all the names there, they are like one group of the prominent statisticians in America. I'm wary of this solution because of the loss of power that comes with decreasing alpha so drastically. This 0.05 is not just an arbitrary value, it's based on Bayes factor. So the maths behind it is there. But it will necessitate huge sample sizes to achieve any reasonable level of power. They estimate that sample sizes will have to increase by 70%. This is not something that would be feasible in sub-Saharan African research contexts. The fourth solution is that there are various other metrics that we can calculate as well as the p-value or instead of the p-value. One of them is the fragility index. And this is a measure of trial fragility. So it's mainly calculated in clinical trials where the outcome is a binary event, okay? And the fragility index is the smallest value of events required to change statistically significant results to non-statistically significant results. The smaller the number, the more fragile the trial's results. There's been reviews that have applied this index to published trials and found many trials to be very fragile indeed, meaning they don't need many events to switch from being statistically significant to not. This is a statistic that can help clinicians determine the confidence they have in trial results. Another alternative, which I'm very excited about, is called second generation p-values. It's a new concept. And this will help to bring clinical significance and statistical significance together. Second generation p-values do not test a zero null hypothesis, but they rather test an interval null hypothesis. This interval is a pre-specified value based on clinical judgment. It represents the collection of effect sizes that are scientifically or clinically unimportant. The second generation p-value is the proportion of data-supported hypotheses that are also null hypotheses. And fifthly, improved reporting and interpretation. The ASA statement concluded that a good acronym to remember is ATOM. To conduct well-designed, thoughtful research, to accept uncertainty, be thoughtful, open, and modest. Importantly, know and express the limitations of your research by being modest. This will help the public to generate statistics or to separate statistics from clinical importance. Practical solutions to achieve this goal include the pre-registration of trials, which we know is already a necessity when it comes to publishing your trials. It needs to have already been registered on one of the recognized databases. We could also consider pre-registration of methodology of observational studies, specifically to publish your protocol before doing the study. Sharing of data and code is already a necessity in some statistical journals or some medical journals, which require this to be done before they're accepted for publication. Results blind review is a concept where the reviewer of the article for a journal is blind to the actual results. So basically reviews mainly the methodology and the justification for the study and accepts or gives feedback based on the methodology, not necessarily the results. So that would stop reviewers or journals just choosing statistically significant studies and hopefully stop that file draw problem that I spoke about earlier. And then, of course, to think about presenting all your findings and not just those that you're excited about. Other ways that we can improve reporting and interpretation are by following specific guidelines in terms of reporting in protocols and in publications of results of studies. These require a sample size statement with justification and any assumptions on the minimum difference of clinical importance. To focus on clinical relevance instead of statistical significance. Standardized approaches to determining the minimum clinically important difference, especially in disciplines where the outcome measures are not so objective, perhaps like psychology or the social sciences. Sometimes it's difficult to know how much of a difference equates to clinical importance, and therefore standardized approaches by experts in the field would be helpful and meaningful in determining this. Often where your p-values are not statistically significant or your p-values are large, to focus on estimates of effect size and confidence intervals rather. This will help you to distinguish between truly negative results and actually inconclusive results. So whether the clinical importance matches the lack of statistical significance or not. So whether a type 2 error has been made or not. To consider abandoning p-value thresholds of 0.05 or whatever threshold, and rather using the p-value and reporting the actual p-value as a continuous measure. And to change our way of teaching and doing research to careful statistical thinking, in the hope that as statistical significance is used less, statistical thinking will be used more. So in conclusion, we need more evidence-based scientific thinking in research. We need clinical relevance to be evidence-based. Statistical significance does not necessarily equate to clinical importance. It's very important to define a priori what you mean by clinical importance and to look at your results and see whether they have met that criteria of clinical importance as well as or in conjunction with the statistical signal or the p-value that you get. Statistical reform is needed, but these paradigms have been in place for a very long time and they're so ingrained that old habits are often hard to break and it's going to take a long time to implement. It won't be overnight. So what does this mean for you, the researcher? Well, what it does not mean is that everything you know about statistics is now out the window. It's just a readjustment of the processes in a more thoughtful, scientific, and evidence-based approach. If you aren't already doing this, start thinking less about hypothesis testing being a mindless set of steps to follow, and rather about how it might be one of a set of tools to help you answer a research question. Also, in the context of observational studies, do more well-conducted hypothesis generating or exploratory studies, especially if this is a new area of your research that you're not sure about the clinically important effect size. There's nothing wrong with doing descriptive studies, with doing exploratory studies. In fact, that is encouraged more and more rather than these hypothesis testing studies which at the end of the day might lead to false information and be more damaging in the long term. It's about a move towards doing thoughtful, evidence-based science. In conclusion, the ASA statement concludes with no single index should substitute for scientific reasoning. I thank you, and I ask you now if there are any questions.